All right, so now that we've done the heat capacity of indium, let's go on to the heat of fusion of indium. So here's the handout. Okay. And you'll have a spreadsheet that you need to download again. This is the Excel that has the heat of fusion of indium, the data for determining the heat of fusion of indium. So go ahead, open that template, and then download it as a Microsoft Excel file, and open the file. This one. Okay. All right. So in this Excel file, you're going to see how the computer automatically analyzes the data. There are screenshots that shows the determination of the melting point and the heat of fusion of indium using the software that came with our instrument. So let's zoom in on the pictures and record the melting point, the onset of the endotherm, and the heat of fusion of the endotherm multiplied by appropriate conversion factors. So your analysis in number 2 should agree with these. Okay, so what do we have? Let's see. Yeah, let me close this one first from the heat capacity data. So this is our template for this one, for the determination of the specific of the heat of fusion of indium. Okay. If you look at the additional sheets here, you can look at the automated analysis, and there's a zoomed in of the automated analysis. So right here, that's a screenshot. Okay. This is a sample of 10.54 milligrams of indium program from 110 to 120, 20 degrees per minute, 120 to 180 at 10 degrees per minute. Okay. And if you zoom in on the data right here, the green curve is the endotherm. So what does it say? The onset of the endotherm right here is given as 157.0 degrees Celsius, right there. And notice there's a baseline that is drawn underneath. Okay, that dashed white line, straight white line. So the area between that white line, that baseline, and the green curve is the heat of fusion. The area of the endotherm is 25.8563 millijoules per milligram. And we should be able to get more or less that number if we do our analysis of the data in this Excel sheet. Okay, so let's look at the data. This is the data. Okay. And so first thing we need to do is what? It should have the raw data for the run from 3 to 6 minutes. So I cut off the rest of the data. I'm only focusing on the data from 3 to 6 minutes because that's where the endotherm occurs. Okay. So the actual times that the software put out are given here in half seconds. It's kind of a weird way of reporting the data. This 1800 means this is 180.0 seconds into the run. Okay, that's what this heading means. I don't know, it must be a Japanese thing. Okay, and this 180.5, so 1805 is 180.5 seconds into the run. So what time after the run started is 180 seconds? How do I convert that to minutes?
Divided by 600.
60 minutes per second, right? So this one, but I have to divide it by 10 first because it's actually 180.0 seconds. And then I divide it by 60. Yeah, so you divide by 600. So I divide by 60 seconds per minute. So that's in minutes. So I can copy that down. So these are the times, right? If you want, you can put more decimal places there. And see the change in time. Okay. Now, what else do we need to do? Let's see. You calculated the time in minutes, so you divide by 10 and then divide by 60. Let's calculate the slope of the y-intercept of the baseline in cells F3 and F4. Okay, we're gonna take the baseline as the line joining the data point at 3 minutes and at 6 minutes. Okay, let's graph this first so we can see where the baseline is, okay? So if you click on this chart, you go chart design, select data, add. We're gonna plot our endotherm, uncorrected endotherm. Uncorrected DSC, okay? So let's just call this DSC uncorrected. Okay, and our X values would be, we're plotting it versus time, so minutes. So from 3 minutes to 6 minutes. Long data set. Okay, that's 3 to 6 minutes. And our Y values would be the DSC, so it's going to be column D. This is in microwatts, okay? There it is. Hit OK. Looks like our baseline is around negative 2000, huh? Let's change the chart option here so that it only shows markers. So let's change the chart type, change chart type so it shows smooth curves, no markers on the points right there. You got it? Okay, so now I'm gonna determine the slope of the line coming from the joining the point at 3 minutes to the point at 6 minutes. How do you get the equation of a line, slope of a line? 2 points. If I have okay, if I have x1, y1, and let's say the other end of the baseline is over here. X2, y2. What's the slope of that line?
Y2 minus Y1 over X2 minus X1.
Yeah, so y2 minus y1 over x2 minus x1. How do I solve for the y-intercept? So this is m, right? Y equals mx plus b. If I want to solve for b, what do I do?
1 minus.
So y minus mx. So I can use y1 minus mx1 or y2 minus mx2, right? I just plug in y and x, corresponding y and x values. So let's calculate the slope of our baseline. So how are we going to do that? Y2 minus y1. So this is going to be equal to y2, the y value at 6 minutes, which is going to be D, column D, the bottom of column D. Okay, there it is, the bottom of column D, that's 370, row 370. Okay, minus the top of column D, which is right here at the 3 minute mark. That's delta Y divided by delta X. So what should be my delta X?
3.
Column B, 370 minus B10. So that would be, the unit for that would be microwatts for the delta Y, minutes for the delta X, right?
Yeah.
This formula? That's okay. And that's what it says in the handout too. All right, so now how do I calculate my y-intercept? I'm going to say equal to m, right, times x. What's the formula for y minus mx, right? Yeah. So this is equal to y. So I'm going to use y1. It's easier to point to it. Minus m times x1. Minus 1931. That's in microwatts. That's a unit for y. You still with me? Okay, so now, yes. Okay. Over here, this is not really 1800 seconds. That's 180.0 seconds. That's just the way the software tabulates it. So, and this is not really 1805 seconds. It's 180.5 seconds. So that's why we have to divide it by 10 first to make it seconds, and then divide by 60 to convert it to minutes. Okay. Yeah, that's the way they labeled it. I guess that's a Japanese thing. Like I said, it's a Japanese software. Took me a while to figure that one out too. All right, so what's the equation? Let's calculate the baseline at these times. Okay, so what would be y equals mx plus b, right? So equals m, which is our slope. What do I do with that? $sign times x, which is the time, right? Plus b, which is the y-intercept, and $sign. And that's our end of term baseline. Okay. And let's add that to our chart. So here I'm going to chart design, select data. I need to add, I'm going to add the baseline. And my x values are going to be the same, right? What is it? To 310?
370.
370. So x values would be time from B10 through B370. You could have just typed B10 colon B370. Okay. And then the y would just be the baseline, right? So these would be our y values. Column E. Hit OK. OK, one more time. And you can see there's your baseline right there. Okay. Now the area between the baseline and the term is the area under the curve. That's going to be the delta. That's going to be the delta H of fusion of your sample. So how do I correct for the baseline? Just subtract the baseline, right?
Yeah. B10 minus B10.
Yeah. So this is equal to B10, which is the uncorrected one, minus the baseline. That's the corrected one. You can see that should be 0, right? At the edge. And then copy that down. And let's plot that in the next chart, the corrected one. Is that where I want to plot it? So chart design, select data, add, corrected DSC. Corrected. And X values would be, again, it's gonna be column B to all the way to row 370, B10 through B70. This is a new chart on the second chart at the bottom, below the first chart. And then our Y values would be column F this time. Okay, and then okay. And you can see that's what it looks like. It now goes to 0, right? Let's change our chart type to corrected DSC scan. Change chart type to smooth lines. Right there.
Is that one data?
So far, yeah.
What was the formula for the y-intercept?
The y-intercept is just y1 minus mx1. Got it? Okay. So now let's calculate the area of the trapezoids in microwatts Kelvin. We're going to use delta T instead, okay? Our X. Remember, our X, our time and temperature are proportional anyway. So let's just do it microwatts Kelvin. So this is going to be equal to, what would be our first trapezoid? Using the corrected values. They are equal to the average of these two neighboring data points, y1 plus y2 times delta x, which is t2 minus t1. Now I may be wondering, this is in Celsius. Why am I using Kelvin?
Because you just subtract.
Yeah, the 273 will just cancel out, right? So that's area of your trapezoid. And then copy that down. So microwatts for microwatts times Kelvin, right? That would be the area of the trapezoids. And sum of the areas in microwatts Kelvin would be equal to sum, right? For which one? Okay. This is F10 minus F10 plus F11, the average of the two, times C10, C11 minus C10, that's the delta T. Okay. So now you say this is equal to the sum of all the trapezoids. So sum from G11 to G, what's it? 370. Ah! Close parentheses. So that is your sum of all your trapezoids. That's in microwatts Kelvin. Okay. What's delta H of fusion in microjoules? Okay, let's convert our unit. What was our unit? Microwatts times Kelvin. So that's microjoules. Whatever you have, right? Micro is 10 to the negative 6 joules per second, right? Times Kelvin. How do I change that to just joules or microjoules? Am I just doing microjoules? Okay, so it's just microjoules per second. Let me fix that. This is just microjoules per second times Kelvin. I have to multiply this by seconds per Kelvin, or divide it by seconds per Kelvin, or divided by Kelvin per second, right? I don't have Kelvin per second. I have Kelvin per minute. What's my heating rate? 10 degrees per minute?
Yeah.
10 Kelvin per minute. So, and then 1 minute is 60 seconds. So minutes cancel out. Essentially, you end up multiplying it by 6.
Okay.
10 over 60. So whatever this becomes, when you move it up, that becomes 60, right? 60 over 10. So you multiply it by 6 to get your answer. Your Kelvin will cancel out, right? So that cancels out Kelvin, and that cancels out seconds, and minutes cancel out.
On the screenshot, it ended up not being negative anymore. Is there any?
Oh, okay, yeah. Because the area is negative,
Yeah.
but for an endotherm, delta H is positive.
We just throw a negative in there.
Yeah, just throw a negative in there. So this is gonna be equal to negative of the area, right? Since you have an area that is negative, you take the negative of the area because this is an endotherm. So minus this number times 60, right?
Just 6.
7 times 6. Okay, yeah, 6. That's right. You multiply by 6. Yeah, 60 over 10. That's the delta H of fusion for your sample. What's the delta H of fusion per gram?
No, we
You just need to know the mass. Here's the mass right here.
So
So delta H fusion, that's microjoule per milligram. How do you convert microjoule per milligram to joule per gram?
times 10 to the 6 times 10 to the minus 6 for the milli.
Microjoule per gram is 10 to the negative 6 joules over 10 to the negative 3 grams.
So it ends up being 10 to the minus 3.
10 to the negative 3 joules per gram. So you multiply the thing by 10 to the negative third, right?
Like that.
Multiply by 10 to the negative third, or
Divided by 1,000.
divide by 1,000, either way. So that's 25.7 joules per gram. That's the delta H of fusion of indium. What is that per mole?
So we gotta multiply by the mole.
Which is how many grams per mole? Joules per gram times grams per mole, right? What's the molar mass? 114.818.
Okay. 114.818.
114.818 grams per mole. So that is your delta H fusion in joules per mole. Let's look it up.
For
This one. The actual delta H fusion for the actual sample divided by the mass of the sample. And then that's microjoules per milligram. To convert that to joules per gram, you just divide by 1,000. Okay, so delta H fusion literature value, let's look it up.
0.27 kilojoules.
Heat of fusion of indium. 3.263 kilojoules per mole. So 3,263 joules per mole, right?
3281.
Okay.
Different source.
Different sources. This is periodictable.org. You can just specify your source. Was it 32? What did I find? 3263? 3263 joules per mole. So I can calculate, you know how to calculate percent error. That's pretty close. All right, so And that's it for today. Save your work. You have to do
It
it.
says you know how to do it.
You know how to do percent error. Save your work and then upload. This is part 2 of your lab performance for today.